So here is a summary of computing line integral. I'm doing this because I think it's going to help you in the test. So problem is usually here's a line integral and compute this line integral, right? That's usually you have phase and you have multiple different ways to go. So I've listed down in here. And all this thing is under the condition there's no denominator. There's everything is defined okay. If it is not, then there's more to think about. It gets too complicated. So try to make it simple in here. Computing line integral, right? The very first method is a direct calculation. Who remembers what I mean by this direct calculation? You're not using fundamental theorem of line integral, not using Stokes' theorem or Green's theorem. Then how can you calculate? Right, you have to use a parameterization of, and you put dx dy, and you actually enter a b dt thing, right? You actually calculate that honestly without using anything. So if the vector field given is a path independence, right? Then we have a tool. And before, at the beginning, it took many different ways to determine whether it's path independence or not. Now we have a very quick tool which is called curl, right? If your vector field is given, if you compute the curl, if it is 0, you know it's path independence, right? And if your curve is not closed, meaning that you started here and ends somewhere else, not coming back to where it started, then fundamental theorem of line integral is helpful, right? Because here's a vector field. You don't know if it is a gradient vector field or not, but by doing that, you quickly realize that's gradient vector field, and you actually compute the potential function, right? That wasn't too bad for, especially for 2 variable. 3 variable, the example they have in the book is not too complicated. So we calculated this with actually integrating multivariable function, potential function. All right, if the vector field is given, you did the curl, it is not 0, then you know it's not path independence, right? That's the test if it is defined everywhere. Make sense? And if the curve is closed, then we have a second tool. Number 1 was Green's theorem if it is just a two-dimensional case, and we have Stokes' theorem if it's 3-dimensional case. Right? The curve C is parameterization involves several formulas like this. Then maybe you're going to consider the parameterization of region D is a lot easier. Then this integral is a lot easier to handle in terms of calculating quickly. It's all about closed curve. All right? If it is 3-dimensional case, parameterization of C, like parallelogram, involves 4 different parameterization, versus S is very convenient parameterization with SP plus TQ, that thing that parameters in parallelogram. So this integral is a lot easier. Then you pass through that. So this is 2 criteria you have to think about: path independence or not, and is it closed or not, right? If you combine these 2 conditions, there are 2 more conditions, right? Not fall in here. And what do you do with that? You just go ahead and calculate it directly. That's a summary of calculating line integral. All right? This is two different things. Path independence or not, we have 1 tools for each of them, depending on this closed or not. Picture make sense? Okay. So you have that there on the slides. So here's the